Okay, welcome everyone. It's great to be here at Reboot Develop Blue. Our session today is called Some Seriously Explicit Lessons in Vulkan. My name is Alon Or-Bach. I'm from Samsung Electronics. I'm here with Karlo Jež from Croteam. We're going to be talking about our journey to create more efficient pipelines in Vulkan and the experiences we've learned along the way. So a quick bit about my team. I'm in the Samsung Galaxy Game Dev team. We support game studios across the world, both remotely in our offices and on site. Primarily, a lot of our time is spent promoting the use of Vulkan on Android, and we will be explaining why in this session. And we help our partners optimize their game titles through the use of best practices, and that's what we're very keen to share here today, and we do in other conferences as well. And these are some of the titles that we've been working on recently, which I hope you're familiar with. We're quite a friendly bunch. Despite all those photos, there's only around 30 of us across the world. We are very busy. I could try and list all 30 of us and thank every single team member, but I want to in particularly thank Michael Parkin-White, who put together the material for this slide deck and presented it. Done a lot of the work alongside myself with Croteam. So today's session, we'll be talking about the lessons that we gained in Samsung from our work in Cirrus Engine, as well as the plans that Croteam has with Cirrus Engine. We've been actively working together with Croteam on porting Cirrus onto Android and optimizing it to get the best performance. And that's one of the key things. We use Vulkan to get the best possible results on Android. A key thing of how our team works is we're very evidence-based. We use a variety of tools to profile game titles when we get access to them, including the ones listed here on your screen. Samsung Galaxy flagship devices use two chipsets, depending on which market they're sold in. You can either be based on the Samsung Exynos SoC with Mali GPUs or the Qualcomm Snapdragon SoC with Adreno GPUs. And depending on which one of these you're profiling for, you should use different tools. And today I'll be talking about our experience using Streamline. So Streamline it comes from ARM. It provides CPU information for both chipset variants, but importantly, it provides GPU data for our Mali-based devices. And it takes a capture like the one here of CPU, driver, and hardware performance counters into a trace. And this gives us a really good starting point when profiling, figuring out how the workload is being executed. So in this trace here, we've picked a couple of key activity counters. In this slightly shaded area, you'll see that's one frame that we've got, so a full frame being rendered. And you'll see that the second row in orange is the vertex activity in the second row, and the third row is the fragment activity. Now you'll notice that they're almost completely interleaving, and this is an example of poor pipelining. We call it pipeline bubbles, and these gaps in the workload are an issue for us. Because despite most mobile GPUs now being unified core architectures, they still really benefit by having a saturated workload, which enables efficient job scheduling and use of specific units. So we really want to make sure the GPU is steadily fed work. But because of this, our frame cost is a mega whopping 62.5 millisecond at our first capture, resulting in running at only 16 frames per second. So in Vulkan, we use various synchronization primitives to coordinate the rendering work. The driver cannot make any assumptions on the dependencies. It's up to the app, up to the engine, to define them explicitly. And if you contrast this with OpenGLES, where the driver has to figure out if dependencies exist and heuristically determines which stages can or cannot be overlapped, sometimes manages to get efficiencies, sometimes doesn't. A pipeline barrier creates an execution dependency between two pipeline stages. The destination stage is blocked until the source stage completes. Now, Serious Engine uses pipeline barriers to synchronize, but you could also use subpass dependencies to achieve this. I'm not going to go into that detail. I refer you to one of Tobias Hector's many talks about keeping the GPU fed if you are interested. So let's take this example. So this is not from Serious Engine. We've got an example here with two passes, a shadow pass and a main pass. And the main pass has a dependency on the shadow map coming out of the shadow pass. So we know we need to have some sort of execution dependency between these two passes. So a naive way to achieve this would be to put a pipeline barrier that blocks the top of pipe of the main scene until the bottom of pipe of the shadow pass is completed. That guarantees that all work on the main scene is held until the shadow pass completes. That, however, results in a total execution time of 28 milliseconds, and we can do better than this. So these are the two passes, the shadow and the main pass. We know, however, that the app only needs the result from the shadow map for the fragment shading in the main scene. So there's no need to block the main scene's vertex work, and we have therefore got an opportunity for the main scene's vertex work to occur in parallel with the shadow pass being executed, resulting in far better utilization of the GPU. So how do we achieve this? We set a pipeline barrier with a destination stage of the fragment shader, and then we hook it up to the source stage of the color output of the shadow pass. And that we know is the work that is actually required, the data that's actually required for the main render pass to result in correct behavior. So what this means is that the bits highlighted in lilac-y purple can be executed at the same time. They're not blocked on each other. So let's see what this results in. You'll see that the main scene's vertex pass, which takes 6 milliseconds, is now able to execute immediately after the shadow pass vertex work is done. It could even happen at the same time. That just happens to be how we ended up seeing the results when profiling. And this means that there's a potential 6 millisecond speed up in execution time because that work is happening in parallel. So going back to Serious Engine, this is the trace we showed earlier. Applying the same optimization in Serious Engine, we see quite a dramatic improvement. You'll notice that the vertex activity is a lot more saturated. There's far fewer pipeline bubbles occurring. Now, the mobile architectures we deal with, especially the ARM architecture, simultaneous arithmetic texture and load store work is highly desirable. Vertex work is most often ALU bound, and fragment work is most often texture bound, and you can benefit by having these occur at the same time, and resulting in a more power efficient use of the game. In our scene here in Serious Engine, we got a dramatic increase of 56%, a 22.5 millisecond drop in execution time. But let me explain why we were able to do this. So Serious Engine is a quality AAA engine, and I promise you I'm not just saying that because I'm on the Croteam sponsored stage and there's an army of Croteam engineers glaring at me. It is a really high quality engine. However, it is designed to be a console desktop engine, and it is performance tuned for console and desktop GPUs, and that can result in poor performance on mobile. And one common example we see in Serious Engine is a large amount of vertex work which is being executed. And that's actually something we see very often across console engines because vertex work is not as expensive on console and desktop as it is on mobile. On mobile, it is kind of our nightmare to have a ton of vertex work happening. So what we can see here highlighted in both the vertex and the fragment work is how much load the depth prepass is taking. So for mobile tilers, a lot of the benefit that the depth prepass provides is actually a burden. The tiler is already going through the geometry, and doing a separate depth prepass is actually additional work, whereas it's an optimization on immediate renderers. So what Michael did in his experiment was looking what would happen if the depth prepass was removed. Now, big disclaimer caveat, if you just remove this, you lose a bunch of effects. So depth-based effects like fog would have to be turned off. However, we are looking to see, can these be done in more efficient ways for mobile? So having a separate subpass just for these effects, as opposed to taking the full hit on the depth prepass. Similarly, occlusion queries do take up a big chunk of vertex work, and that's something we're looking at, whether there's other ways to achieve the resulted effects they provide. So based on the work we did with Series Engine and the scalable shader system that Croteam developed, we've been experimenting to come up with a good model for handling the large numbers of shaders efficiently. Another disclaimer, as Karlo will soon explain, this is still very much a prototype that we're evaluating. So AAA games typically have thousands of unique materials, lots of dynamic object updates. GPU memory management can be rather tricky, as we are now learning in Vulkan. So after giving that responsibility to the game engine, it isn't a simple problem to solve. The goal we're looking at here is to create a blueprint tailored for Vulkan that would handle such a shader system and deal with all the large numbers of shaders, and try and provide a simple design for easily updating uniforms universally, no matter which shader is used, and minimize descriptor set updates. We also want to try and achieve a small number of rebinds between draws. And finally, we really want to avoid dynamic memory allocation mid-frame, because that's an expensive operation, and suddenly your game will stall and jitter, and we do not like that. So the solution we've come up with, shaders need to access live uniform data, like object transforms, camera properties, material attributes, etc. Rather than creating a new VK buffer every time we need to modify this data, we allocate a large buffer per shader stage up front, and then that maps that maps to what the app is using, and the app is responsible for managing it. The uniform data gets stored within this buffer, like above there. And once we've reached the bottom of the buffer, we go back to the top, we wrap around, and override data no longer used by the scene. And we found anecdotally from all our evidence that one buffer per shader stage is a good sweet spot, because it minimizes the amount of unique pieces of data that we have to update, because vertex data tends to contain a lot of repeated information, such as scene properties, and then that can be reused by different shaders or objects. A benefit of mobile is mobile memory is unified. You have a unified memory architecture, so you can map you can create the VK buffer using mappable memory, and then map it and blat it from the CPU without having a copy, because it's the same actual memory. On desktop, however, you can't do this. You need to create a staging buffer, so having a separate copy, and then you use a command called vkcmd copy buffer to incrementally update from the one that your host owns to the ones of your device. However, there's benefits because desktop GPUs tend to have a transfer queue that can deal with that very efficiently. So that's a plus there. But you can ignore that because that's desktop, and desktop doesn't matter. That's a joke. When writing out the uniforms to this buffer, we keep track of the offset, so where the data has been put, and we use that when we bind the descriptor sets in the command buffer. So how does the mapping work in the shader? If you can see here, this is a very simple bit of shader code, so shader.vert. And this is the round-robin buffer for vertex work that I mentioned earlier. So based on the uniform data that the shader requires, we create a set of descriptor set layout bindings. And these descriptor set layouts are used to describe the structure of the shader and what uniform buffer objects it's expecting. And we set the type to be dynamic, as it will be dynamically updating these descriptors. For each of these layouts, we need to allocate a descriptor set. And that comes from a descriptor pool, and that memory for the descriptor pool was allocated before we got to our frame loop. So away, again, expensive operation, you do that away from your frame loop. Then we need to update each descriptor to point to our round-robin buffer, and we're ready to go ahead and use our vertex shader bindings. Similar for the fragment shader, just a different set of bindings for the different uniforms it requires. So now we get to a nice, beautiful visual example of this. How would this actually impact a scene? And just to be absolutely clear, this is not a scene from Series Sam 4. I was asked to say that by the artists. In this scene, we have 4 independent objects and 2 material types. So, first we update the uniforms, which is accomplished by writing out data to one of our desired buffers. So you'll see here the scene properties and camera properties appear in the fragment and vertex uniform buffers accordingly. We repeat that, and then we bind our opaque material pipeline. So that's our bind there. So that binds it to a VK pipeline which contains the shader that we've compiled. So next, we need some more uniform data to write out from the material and for our house. And we bind that. And when we bind that, so if you see, that's the point where the shader knows where in memory to pick up its uniforms from. And then our command buffer, after doing that bind, gets to execute, and we have our house on our frame buffer. So next up, we draw the terrain. So again, we're updating updating uniform data here for the material. But because this object is using the same material as our previous one, we don't need to update the scene or camera properties again. That's still there from the previous render. We only have to provide offsets that are different, like this one. And that reduces the work both for our application and for the driver. So it reduces having to compute new offsets, rebind uniforms, etc. And note that we've chosen this specific draw order because both materials are opaque, then it reduces the need for rendering the beautiful terrain that we got behind it. And finally, we draw our trees. We're now having to switch to a new pipeline because this is a transparent material pipeline for the leaves. Any descriptor sets that have been previously bound with the previous VK pipeline, if they match, they remain bound. If they don't match the layout, they become unbound. And in our case, we have to rebind most our uniforms. So we update our objects, we bind them, we draw a tree, we update the uniforms again, we rebind them, and we draw our second tree. And one more comment here that I do seriously hope that any Croteam artists with us today appreciate the photorealism of these grass blades. I know how much you care about your grass blades. So, sampler uniforms are a little bit different, and this, a couple of caveats. We don't have a mechanism in core Vulkan at the moment to dynamically update in a command buffer until we get to bindless descriptor indexing, and that's kind of, there's currently a multi-vendor extension to do that, but current hardware does not universally support that. So we need to pre-bake descriptor sets for any combination of textures or samplers that we want to use. We allocate a descriptor pool to store our bindings. And then we do that again early on. We don't want the descriptor pool memory allocation to create a hitch in our frame loop. Then whenever we encounter an object that uses a texture sampler, first we create a descriptor set layout. And this is just like what we did before with our other uniform data. In this case, we've got the 3 sampler bindings for texture, diffuse, texture normal, and texture specular. However, we'll get to this when we get to the bottom. If you've already created this earlier, you don't have to again. Next, we create the descriptor set from the pool. And if we found it because it's already in there with a hash we're about to create, let me just put these full up. If it's already there because of a hash, we don't have to do that again. Thirdly, we update the sample bindings to point to the specific image resource we need. In this case, we're drawing a hedgehog onto the scene to update the descriptors with a descriptor image info structure that points to those images that would have been created earlier. And finally, you bind this all together, binding the descriptor set. When you compare this with OpenGLES, this process has to happen every draw call. There's no way to tell the driver whether or not your sampler is changing or not. And that overhead is what Vulkan really reduces. One last note. When you hit your descriptor pool limit, when you've maxed out your memory, you've created too many descriptor sets, then it is far more beneficial to reset your descriptor pool and recreate those than allocating a new one on the fly, again, to reduce the need for dynamic allocation of memory when you're doing expensive rendering. So on that note, it's my pleasure to hand over to Karlo, who will be talking about what's in the pipeline for Cirrus Engine. Thank you.
Thank you. Okay. You can sit now.
Thank you.
Does this work? Yeah. So yeah, my name is Karlo Jež. I'm an engine programmer at Croteam, and recently we've been working on pipeline creation in Cirrus Engine, and this is what I'm going to be talking to you about. So what's the problem? So pipeline creation is slow. We've known that it was slow back on OpenGL, but with that API there was nothing we could do about it. Same goes for the older versions of DirectX. But with, this all changed with modern APIs like Vulkan. So one of the things that Vulkan has is the VK pipeline cache, which caches the already created pipelines. But this will not help with the first impression, because the first time that you load the game, it will stutter. First time you open a level, it will stutter. New scene, stutter again. So a lot of stuttering, basically, and especially on some platforms. So our solution for this was to move pipeline creation from render time to load time, when the game or level is loading. So the point from where we started was our old graphics API, which was made years ago before the modern APIs like Vulkan. And there, the pipelines could only exist in the low-level graphics code. It was done so that various inputs and state setting functions would be called all over the code. And when you issued a draw call, we would actually combine all those inputs, calculate a hash, and then see if that pipeline state maybe already exists. If it does, then we use it. If not, we create it. And this is the process that we need to do every draw call. But the problem here is that since the state depends on so many external variables, there's no way of knowing which pipeline you're going to use until you actually issue that draw call. So this became a huge problem when we started working on Telesport for Xbox One on DirectX 12 and later for the Nintendo Switch with Vulkan, where pipeline creation was very, very slow. But fortunately, since those are consoles and have fixed hardware, we could actually ship the pipelines themselves, the caches, with the game. So what we did is that we created a sort of a renderer that actually rendered all the objects in the game as they were loading. So every model, every decal, every particle effect was rendered under various conditions, so all the possible combinations of lights and everything. And that gave us our pipeline caches, and it was good. The games worked quite well, but the problem was that we couldn't still be 100% sure that we've covered all possible cases. So, and that's because the pipelines that we use were the result of the states that we set externally, instead of having the state be the result of the set pipeline as it is in modern APIs. So this experiment led us to the design of the new system. In the new system, pipelines are first-class citizens. They can be created by the high-level code using generalized API-agnostic descriptors. And they can even be, after they're created, they can be for some more simple effects like a GUI or HUD rendering. They can be bound directly and used for drawing. But more generally, for more complex objects like models, they are organized in hierarchical state caches that are created when these resources are loaded. So what we've noticed and known before is that a lot of parts of the pipeline state are constant and do not change when, for example, any particular model is being rendered. But there are, on the other hand, lots of other parts of the state that changes depending on the circumstances, various lighting conditions, etc. And for each such different circumstance, we need to create new variations. Yeah, and there are a lot of these variations, and controlling their number and reducing them to a lowest possible number is going to be a huge effort with this. It was and it will be going forward. One other important feature that we wanted to have is that we didn't want this, the work on this to slow our designers down, because loading pipeline states would severely possibly increase loading times, especially now since we have too many states still. So what we did is we have delayed creation, where the caches are actually created, but the pipeline states are only created as needed. So let me show you like a simple example of a one pipeline cache. So it's let's say we start with a model. Each model has a number of surfaces. Each surface defines a set of possible vertex inputs and has a material. Each material has one or more shader passes. Each of those shader passes then further defines the state. And for those parts of the state that remain undefined, we need to create more variations, of course. So for example, let's say that we have a model that has a double-sided surface, so both the front-facing and back-facing polygons are rendered. In that case, we don't need additional variations for polygon culling, but if we have our regular model where the back faces are culled, we need another variation where the front faces are culled, because it might possibly be flipped or rendered in a mirror. One other thing about the hierarchy design is that if any part of the hierarchy is modified, for example, say in the editor, we can easily invalidate the entire cache. We knew from the start that this entire system was not going to be built and finished overnight. So we knew that both the old system and the new one will have to exist side by side for quite a long time. There's another interesting thing for us at Croteam is that we try and support all our older content and try to make it work with the newer versions of the engine. But what this means is that we have a lot more content to support. So what we did with this system is that we decided to implement this for our newly made node-based PBR shader that we designed for SAM4. And this one uses the new system. But all the older shaders for the older games still use the old system. So we need to work with that until everything is ported over. Another important fact was that designing such a system will cause problems, visual issues, and we wanted to minimize that as much as possible. So one of the ways that we did that was the on-demand pipelines. They are actually created from the bound inputs and like parts of the states from the cache, but mostly from the bound inputs. And in some way, they are a hybrid of the old and the new system. And what we're using them for is two things, which are related, as a fallback and for validation. So what's going on is that, for example, if an artist is working on something and the pre-created state is wrong because someone made an error, let's say me. When they will not see the problem, most likely, because the fallback would be used instead of the provided state, because the engine's validation system would detect, oh, this is not right, there's something wrong there. But at the same time, this issue would be logged so that we know that there was a discrepancy even though it's not visible. And this logging was really an important part of the work because compared to visual regression testing for any kind of problems and differences, it's much superior. So visual regression testing is very hard and prone to errors because you need to look at the differences, and with pipeline states, they might sometimes be very subtle visual differences between, for example, if a wrong shader was chosen. Sometimes it's glaringly obvious, but sometimes it's not. One other part is that we try to reduce the duplicate code paths that result from having both systems as much as possible, but it's not always possible. So for example, for decal rendering, we apply a small depth offset, so there's no z-fighting. But since depth offset is part of the pipeline state, it needs to be set when the states are created, say when we're using the new system. But if we're using the old system, then we need to have it set during rendering. So our solution for now, until we get rid of the old system, is to actually do both. So we set it both during pipeline creation and during rendering and use our internal validation to check that everything matches. So like I said, the main problem is fighting with the variations. When we were doing the original Xbox One port, we found a lot of variations where we did and didn't expect. So it all depends on the flexibility of the rendering system. The more flexible it is, the more potential for more pipeline states you have. And some systems, unfortunately, need to be flexible. So, for example, our decals can be put over any kinds of surfaces because we make shooter games and you put bullet holes on anything. And you need to be able to put bullet holes on anything. So these models could be animated or not. They can have light maps or not. And since the system needs to remain flexible, we say, well, the hell with it, we need more states, and we actually made them for decals. But on the other hand, we had like an interesting system where you could actually apply any kind of, it was like a material override overlay system, which could apply any kind of material in the game over any model in the game, and it was controlled dynamically through scripting. Well, this gave a lot of power to the designers to do many interesting possible visual effects, but the problem is there's no way of knowing at model loading time which materials we're going to end up with. So what we did was it changed it so that the materials that are going to be used as an overlay or override need to be stated explicitly in the model itself. So like this is a very, very, very small example. So we have models and materials, and if we only use the ones that are explicitly marked, we lose a lot of the states that we don't have to create in that case. So yeah, like I said, it's a balance. So where we are at currently and what are we still need to do. So yeah, like I said many times, reducing the number of states. And also, when working on new visual features, we now have to think about, always think about pipelines as well. If I have a cool new feature, will that add another variation or something? Then it's probably a no-go, unless it's very, very important. So we need to think about that. Of course, we'll continue removing the older code paths, but it will take a while. And also, we could use this caching system for much more than pipelines. So we can go one step further than what Alon mentioned, and we could actually create descriptor sets at load time. And we could also record secondary command buffers so when the model is being rendered, only the buffer is replayed instead of calculating the entire state all over again. But it's still a long road ahead of us, and we'll see where it takes us. Thank you. Questions? Good. Okay.
Sorry, I've turned this off. I can't figure out how to turn it on again. Yes.
You have like extra slide with info.
Yeah. If you have any questions, I'm guessing you're all saving them up for these fantastic other sessions we still have. Very excited by the next session coming up by Johannes Kuhlmann. It'll be the first session about Vulkan on the Nintendo Switch. At least the first public session, which is going to be very exciting in this room after the break. And then tomorrow, that's your chance to ask any questions you fancy. That's going to be with myself, Karlo, Graham Weirdahl, and Christian from ARM. This will be hopefully a very lively session about the benefits and the challenges of GPU API standardization. Do come along tomorrow morning. And a session from ARM about ARM Mobile Studio, which contains the tools I discussed today, including Streamline, and from Imagination, again, more good experience about profiling with mobile graphics applications. So do come along to these sessions, and feel free to ask questions after as well. Thank you.